All right, this video is going to be talking about 2 and 1 sample t-tests for means. So in the previous lessons, we've introduced to the t-distribution, which is used for means. For estimating means, we used a 1 sample t-interval or a 2 sample t-interval for means, depending on if it was 1 or 2 samples. So we're going to expand upon that using tests. So we're combining 1 and 2 sample t-tests into the same lesson. First, we'll start off with a 1 sample. So a 1 sample t-test for the population mean mu. I want you to pause to read this problem. This problem is talking about seeing if you guys, on average, sleep 8 hours a night, or if you have a tendency to sleep less. Most people's train of thought is you probably sleep less than 8 hours a night. So the hunch is we want to test to see if that claim is true. So we sample some data. So let's say 10 of you give your average amount of sleep per night and report our findings. So in our sample set of 10, we have the following information to display. So one of you said 3, one of you said 5, 5, 6, 6, 6.5, 6.5, 6.5, 7, and 9. So on those 10 data points, we could create a dot plot and kind of visualize where those numbers are. It's important that you have a graph to represent this data when you're checking your conditions. So seeing if the small sample size has approximately normal or symmetric shape is important. We might have some cause for concern here because we do seem to have an outlier up here. But by and large, if you look at those numbers, you're going to take a minute to pause. You're going to enter this data into your calculator. So pause the video, enter the data in your calculator. All right, you should go to your stat menu and put the 10 values in there. Make sure you type them in correctly. And you want to see the mean and standard deviation. So we're going to click Stat, Calc, 1 variable stats. So see if your mean matches up with what I have. From the sample set of 10 data points, we have a class average of 6.05 hours of sleep, which is definitely less than 8. And a sample standard deviation size of 1.55366 with a sample size of 10. So really those 3 numbers are what we're focusing on. So let's reveal those. Our test and the null 8 hours of sleep, that's how we can construct our hypothesis test. So let's talk about what the hypotheses would be. Remember, in a hypothesis test, we want to assume the null. We want to assume the default being 8. Remember, innocent until proven guilty. So for our procedure and parameters, we want to identify what the hypothesis is. So let's see what the null would be. The null would be, and the alternative would be, the null would be HO is mu is equal to 8. But then the alternative would be HO is mu. And in this problem, what direction would it go? Would it go above, below, or not equal to? Think about that. Below is correct. So once you've identified your hypotheses, we want to identify and label what the parameter is. So our mu is the true mean sleep time in hours for all AP Stat students. Remember, in a hypothesis test, we assume the null. So we assume 8 hours of sleep is what people are actually getting. And we're testing to see if they're actually getting less than 8 hours of sleep. So our sample of 6.05 is promising because that's far enough away from 8 that might give us a good p-value to reject the null and assume that the alternative is true. A couple things to consider when you're entering your data. Put in L1. Turn your plot on. We want to see this data and what it looks like. So go to stat plot, second y equals. Because you have your data points in, you'll go to second y equals, you turn that first plot on, and you're going to go down to that box plot. I like the box plots because the box plots show outliers. So if you turn that on, it'll default it to list 1. And remember, you're going to hit zoom 9. And my hunch was correct. We do have an outlier here at 9. So we want to be careful when reporting that data. It's okay to still run the tests and get the numbers with it, but you want to be skeptical of those numbers if those are true. Right? It's better off having a larger sample so we don't have potential outliers, or just having a big enough sample like 30 where it's not a big deal because the sampling distribution would be approximately normal. All things to consider. This is a one sample t-test from you. Again, we use t because it's means. All right, so what are our conditions? Well, you should know those 3 conditions by this point. Random. Do we have random? The problem says there was a random sample of 10 students. What's the next one? Right, 10%. Can we assume that our sample size of 10 is less than 10% of all AP Stat students? Of course it is. And the last one, the approximately normal. That one's a little bit iffy, right? Because we have an outlier, and that's giving us a problem. But we're still going to run the test. Just say proceed with caution. If you have an outlier, it's better to say proceed with caution, or say, well, we got to be skeptical, something like that, rather than just throw the whole thing away and not do it, because you're going to lose more points for not doing it than you are just going to say be skeptical of the data. Okay. So remember, this is your A. This is your assumptions, same as your intervals. Nothing's changed. So let's review those formulas. The mean of the sampling distribution is always equal to the mean of the population. Now, in a test, we assume the population is the null. So at 8 hours of sleep is actually what we're assuming right now the population mean is. So that's what it's going to be equal to. The standard deviation of the sampling distribution is equal to the standard deviation of the population over the square root of the sample size. This we don't know. We're not given a population standard deviation. So remember, when we're not given the population standard deviation, we use our statistics. So we have a sample standard deviation of 1.554. We use the standard error instead of the standard deviation. We calculate the standard error by taking the sample standard deviation, 1.554, and dividing it by the square root of n. N in this case is 10. Pause the video, calculate that out. Make sure you can get the following number that I display. Okay, you should all get 1.554 divided by the square root of 10, which is approximately equal to 0.4914, about 1/2. Your standard error is what that's called, SE, sample standard deviation over the square root of the sample size. That formula is provided to you on a formula sheet. Pause to write this all down if you need to. Okay, so we've done the identifying the hypotheses, the parameter. We have talked about the conditions. So let's go ahead and run the test. Here are your data points again. Now I added the standard error, 0.4914. Remember that our test statistic is what we're trying to find. So it's, in this case, not z, it's t. So in the proportions, we use the z-score. Well, we modify that with a t-score. And it's very similar to what the z-score is. You take your statistic minus your parameter and divide by your standard deviation. Your statistic in this case was 6.05. Your parameter was 8. The parameter is the null. Your standard error is 0.4914. And the reason we use t and not z is because we have a standard error, not a standard deviation. With proportions, we didn't have to worry about that. So calculate that. Pause to calculate. You should get a test statistic of a negative 3.968. It's negative because the statistic is below the parameter. So you're going to get a negative as a result, which means that when we're testing it, we're testing to the left side. Here's the generic formula for that. Sample mean minus the population mean divided by the standard error of the statistic, S divided by the square root of n. I don't use table B for these. I find that annoying. So I tend to use TCDF when I'm calculating the p-value. So to get TCDF, it's the same menu that has normal CDF. You're going to go to second vars. TCDF is option number 6. Oops, second vars 6. In this case, because we have a lower, or we're going below negative 3.986, we're going to leave our lower as negative infinity. Our upper is going to be negative 3.968. Our degree of freedom, that's the sample size minus 1, so that's going to be 10 minus 1, which is 9. And we'll paste it. So we'll put all that in there, and you get a very small number, 0.0016. So recall what that means. When your p-value is very small, what does that allow you to do? Think about that. Let's go ahead and reveal these numbers here. We'll come back to that in a second. Our degree of freedom is 10 minus 1 is 9. Our TCDF, your lower is negative infinity, your upper is negative 3.968. Your degree of freedom is 9. And you get 0.0016. But again, what does that mean? Well, a small p-value is indicative that you can reject the null hypothesis. So if that's what you were thinking, that's awesome. So let's go through and let's go and calculate this using the test mode. So we want to be able to also calculate this test using your stat menu. So we'll go to stat, we'll go to tests. Think about what we're doing. We're doing a one sample t-test. Which one of these options makes the most sense to use? Well, I don't see a one samp t-test, but I do see a t-test. And I see a two samp t-test. So by logic, I'm going to say the t-test is one sample. Now you have two options with tests. With t-tests, you can put the data in, just like the t-intervals, or you can put stats in. So if you put the stats in, you have the 6.05, you have the 1.554, and the sample size of 10. And the null, we have to make sure that that null is 8 in this case. We also have to identify the correct direction. So since this is less than, I have to scroll over to less than and calculate that. Now, why did my calculator auto-populate the 6.05 and the 1.553 and the 10? You want to guess? That's because we already had the data in there. Remember, I calculated my graph and my one variable stats before. So when you have that data in there, you don't have to retype it. Under t-test, if you stay on data, you change your null to 8, you change your direction to less than, you can get your calculations, and I'll go back to draw so I can show you that too. But you get your p-value of 0.0016, same as we got over here. You get your standard, your sample mean and your sample standard deviation and your t-test statistic. So if you wanted to do a drawing, under any of the tests, there is an option instead of calculate, next to calculate, if I can get this to go to the right spot, next to calculate, you can go down and click draw instead. So if I highlight a draw, it'll graph what looks like a normal curve. It's a t-curve, but it'll also graph the normal, the t-distribution with the test statistic and the p-value. Well, nothing seems to be shaded because remember, this p-value at negative 3.9, that's almost to out here. And there's really nothing that would show up on a screen unless that screen was blown up super large. But that is also a very small percentage. That's less than 1% shaded. So you're not really going to see that, but it is going to be shaded ever so slightly here into the left. So what does it all mean? Well, this is your statistical work. And your statistical work doesn't have to be complicated. You can run this test in your calculator using the t-test, report your t-test statistic, and your p-value. Those are really all you need to run the test or to display your work, and name the test, one sample t-test. But again, here are the directions. You're going to go to t-test. You're going to input it from your data. You're going to run the test. And you're going to get the following results. Get all that written down if you need to, and pause, and then we'll move on to the next one. So pause to write. So what's our conclusion? Well, what happens when you have a small enough p-value? That allows us to reject the null. So we have a strong case to say students in AP classes are by and large getting less than 8 hours of sleep. This is convincing evidence because our p-value is 0.0016, which is way smaller than 0.05. It's not even close. That's your summary. You do have to have a summary. Pause to write that down. That's a one sample t-test. If you have any questions, please ask. If not, let's move on to the two. So how do you do a two sample t-test? Well, in this case, we're going to use the same data as before, but now we're going to add another type of class. So you're in AP Stats. Let's compare that to AP Calc students. Here's some data from AP Calc students. Read that, please. All right, you got the idea. You have the sample size of 16, a mean of 6.125, standard deviation of 1.668, and you even got a graph displaying the data, so you can check that approximately normal condition, which it looks pretty symmetric, so we're good to go on that. But we want to compare that to AP Stats students. So we're gonna put our data. I have them both kind of side by side, repeated, just the general stuff what we need. We have the box plot here and the dot plot, which remember there was an outlier, so we want to proceed with caution. And our sample data, sample mean, sample standard deviation, and compared to alongside the AP Calc. And they're very similar. Notice that the mean here is just slightly smaller than the means from the AP Calc. These are really just made up numbers, but you get the idea. When they're very close together, it's not likely you're going to have a strong case that there's going to be a difference. But the problem here is you got to be very careful with your direction, because it says use the summary stats below and the data from number one to test the claim that their students' sleep habits on average differ from AP Stats students. Differ does not mean less than or more. So even though the AP Stats number is smaller for the sample mean than it is for the calculus, the question is saying, is there a strong enough difference? Which means we're not using less than, we're using not equals to in our alternative hypothesis. Let's go ahead and set that up. So that first part of these inference problems is always the procedure and the parameter. So our parameter is the difference of the mean, statistics minus calculus. You could go either way. So you could have done calculus minus statistics, it does not matter. We just did statistics first. That's the true difference in the mean amount of sleep in hours per night for AP Stats and AP Calc students. Now, what is the statistic? Well, those are your samples subtracted. So we have those numbers. Crunch the numbers, pause to calculate it. See if you can calculate that statistic, the sample mean of statistics amount of sleep hours minus the sample mean of calculus minus amount of sleep hours. You should have gotten a negative number, so negative 0.075. Now, let's write our hypotheses. Remember, the null is no difference. The alternative is a difference. In this case, any difference, so not equal to. So for the null, we use the parameter notation, so mu of s minus mu of c. We say it's equal to 0. You could also say mu of S equals mu of C, but we usually just say subtract them and equal to 0. The alternative, mu of S minus mu of C. This is where the not equals comes in because it's a difference. So we have to read the problem carefully. Now, remember, you have to choose that depending on the problem. If the problem says A is going in one direction, you use one of those inequality symbols. And then we identify the procedure. Well, we have 2 samples. So do you want to guess what this one is? This is a 2-sample t-test, not a 1-sample, not a t-test, 2-sample. So our procedure is a 2-sample t-test for the difference in the 2 means. Pause to write this down. Our next part in an inference problem is the assumptions and conditions. So we have to check random, normal, and independent. Those don't change. We check them for both of them. So we have our statistics and our calculus students. We got random, normal, and I said in random, independent, and normal. Independent is the 10%. So random, 10%, and approximately normal. In here, it doesn't say anything about an alpha level, so I always default it to 5%. So let's check for random. Is there a random? Well, it says assume the random sample of 16 calculus students is independent of the sample of AP stat students. So they say there's random in the calculus students. And if you go back to the problem for AP statistics, let me move this out of here. To test your belief, take a random sample. So we have randomness for both of those. So we check those off. We write them down. Random sample, random sample. You don't have to get fancy with your wording. You just got to state that they were random. Now, you know these numbers were actually made up, so they're not really random, but don't tell anybody. 10% condition, sure. We've met that. We state that. 10 and 16 are both way less than 10% of all the AP stats or calc students, respectively. And approximately normal, well, remember in this previous problem, technically the stats is not, there's an outlier, so proceed with caution, but you're going to do the test anyway. And then the calculus students, no strong zero outliers, it's very almost symmetric, so you're good to go. And we're going to go ahead and run the test. Oh, pause to write that down. So let's go through and do our statistical work. This formula is a little bit trickier, right? We have T, and it's the statistic, which is the difference in the 2 sample statistics, minus the null, which is 0. Remember that standard error formula for 2 standard deviations. It's when you square each one divided by the sample size, add them together, and then take the square root. I want you to think about what numbers go in where. That's your numerator. We had subtracted those already. Your standard deviations are 1.554 and 1.668, sample size of 10 and 16. So carefully pause to calculate that and see if you can get the same test statistic that I'm about to reveal. Okay, using my calculator, I did the numerator, which would just be negative 0.75, or negative 0.075, divided by the denominator, and I just typed that all in under the square root. You can see how I typed that in. And I got negative 0.1164, which is consistent with my answer here. So our t-test statistic is negative 0.1164. So let's calculate our p-value. That's going to be TCDF, so second vars, TCDF. And because we have a negative number again, we're going to leave our lower as negative 1.1E99. So Make your upper negative 0.1164. And I want you to think about what your degree of freedom is. Look at your smallest sample size. You got to use the conservative estimate. So your smallest sample size, and you're going to subtract 1. All right, click paste. Now that number represents your p-value if you were going just below it. Now remember, this is a two-sided test. So you have to double that p-value. So think about what happens. If I were to do this picture just a less than, I'm going anything as extreme as negative 0.1164 or less. If you were to do the the TCDF and make the lower bound positive 0.1164 and the upper bound positive 1E99. Keep your degree of freedom 9. Normal curves are symmetric. So we're really in a two-sided test calculating the over and the under, and we're doubling that p-value. So really you're going to have about 90%. So 0.4549 times 2, or add it together with itself, is your p-value in this case, since it's a two-sided test. You always double the p-value in a two-sided test. So let's crunch the numbers. Again, it's going to be 0.4549 times 2, because in a two-sided test, we always double the p-value. And that's going to be about 0.91. Remember, your degree of freedom is a conservative estimate. And let's take a look at this being a two-tailed test, what the picture would look like. You're really calculating the percent under negative 0.1164 and above positive 0.1164. That's a lot of that graph. So you can understand why the p-value is so high, okay? But now that you've gotten all that down, pause to write it, and I'll show you the calculations behind it all. So just to reiterate, we did a TCDF when we're doing the test, after we do our test statistic, can't talk. We do our upper at negative 0.1164, lower at negative infinity. Degree of freedom is 9. That's a conservative degree of freedom. You calculate that, and you get about 0.4549, at which point you double since it's a two-tailed test. But we're also going to use our stat menu, and I know I've harped on our stat menu a lot, but it's because it's easier. It's less work, and in a stats class, you really want to be using technology as much as possible so you can focus on analyzing the data. So our p-value is 0.9098. You already should know what to conclude based on that, but we're going to go through and do the following sequence. Please type this in with me. So go to stat, go over to tests, and because this is two sample, we're going to do option 4, Twosample Ttest. Now we don't have raw data from the calculus students, so we're actually going to go over to stats this time, and we're going to enter our numbers in. So think about what's going to go in where. That first X bar 1, we're going to put our statistics. So 6.05, standard deviation of 1.554, with a sample size of 10. Then we'll do our calculus for the next one. So 6.125, 1.668, and 16. Now, what direction do we go? Remember, this is a difference. We're looking for a difference in the two, so we keep that at not equal. Don't click pooled. And go down to calculate. Now, I want you to pause for a second. Make sure you have the same numbers that are on my screen. And look at what might be different. In fact, I'll keep this here and I'll go back to the previous screen so you can see. Do you notice any differences? Okay, detectives, you probably would have if you've watching this and you've kind of following along with it, you might notice that your degree of freedom, once again, is going to be different. And remember how the calculator likes to mess with those degree of freedoms. When there's two samples, calculator uses a more advanced formula to calculate to get the degree of freedom. It's going to be more precise. It's not going to, it's in my opinion, better. Now, there's nothing wrong with using the conservative estimate. Gives you a more wiggle room, right? But a more precise answer is always preferred. So we're going to use our degree of freedom. There is a slight difference in your p-value. It's not that much, 0.9085 versus 0.9098. So your p-value, notice, is a little bit less, but not too much less. But that's mainly the thing. So when you're doing things from your calculator, you do not want to be writing the conservative degree of freedom. So you're going to do a two-sample t-test. You're going to enter your statistics in. It doesn't matter if you've done the statistics first, then the calculus, or vice versa. You'll still get the same result. You go to two-sample t-test and go down to calculate. And if you want, you can go down to graph, and you can see, let me do that. And move this out of the way. Everything else being the same. If I go down to graph, or draw instead of calculate, look at how much of that is shaded. That's 91% of the graph. That p-value, it's very likely that a sample of that or extreme could happen in both directions. So it's a very large p-value. What does that allow us to conclude? Now, the calculator's test is more accurate, less conservative. Report the degree of freedom from there if you plan on using the stat menu. I encourage you to use the stat menu, use the degree of freedom there. So let's do our conclusion. Let's do our summary sentence. We've done our statistical work. Our summary, large p-value, what does that mean? Well, let's think of this template here. Our p-value of, what was our p-value? 0.909 is greater than alpha. So what do we do when it's greater? We fail to reject the null. We reject it when it's smaller. We fail to reject when it's greater. There is simply not enough evidence. There's not sufficient or convincing evidence, not even close, to conclude that AP Calc students and AP Stat students differ in the mean amount of sleep they get. And to be honest, even if you did a one-tailed test and said AP Stats was less at a 45% p-value, it's still not enough difference in not enough to conclude. And that should make sense. These are similar students getting similar amounts of sleep. Everybody's stressed out. There's really not a difference between the two. But now we have data to back it up. Pause to write that out. Well, that concludes the lesson. There is let's summarize the important ideas, and you can try to check understanding on your own. So the important ideas, we got our parameter. Our mu is always going to be the true mean, or the difference in the two mu's is the true difference in the means. Always use context. We have a procedure. It is either a one-sample t-test for mu or a two-sample t-test for the difference in the mu's. In your calculator, you're going to either do stat test 2 or stat test 4. I'll write that out. Our statistic is going to be either the one sample statistic mean or the difference in the two sample means. Our conditions, same as before, random, normal, a random 10%, approximately normal. Nothing's changed. Write those down. Our test statistic. Now this can get a little bit tricky, right? For a one sample, it's going to look like this. Our t is the sample mean minus population mean, which is the null, divided by the standard error. Remember that this is the null. So when you see mu here, whatever the null is, that's your test statistic. For Twosample, it's the difference minus 0 divided by the combined standard error formula, which these two are on your AP Stats formula sheet. The recommended method that I say to use is use the calculator. When using the stat menu, report the degree of freedom given there, not the conservative n-1. So your p-value is going to be using TCDF. You have a lower bound or upper depending on which direction you're going. But you can avoid using TCDF and figuring out that direction if you use your stat menu and report the degree of freedom there. Pause to write that out. Okay, so this is your check your understanding question. Pause to read this, please. All right, here's our scenario. We have the level of dissolved oxygen, DO, in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the DO level at 30 randomly chosen locations along a stream. Here are the results in milligrams per liter. The sample mean is 4.77 and the sample standard deviation is 0.939. We have an average dissolved oxygen level, which is below 5 milligrams per liter. It puts aquatic life at risk. That should be a puts there. So anything below 5 milligrams per liter puts aquatic life at risk. Our sample is 4.77. Do we have data convincing enough to provide evidence at the alpha equals 0.05 significance level that aquatic life in the stream is at risk? So think about what the null is. The null is the default, what we assume is true. And then what we're trying to prove is the alternative. Let's see if you can do this on your own. I would really click to pause to try on your own. When you're done attempting it, doing the 4-step process, then check along the way. Make sure you have everything here. So what do we need? Well, we need to identify what this is. There's only one sample here, so it's a one-sample t-test. What is the mean? It's the true mean DO level of the water in the stream. So the true mean dissolved oxygen level in milligrams per liter. Circled here, I have my hypotheses. Anytime you do a test, you should always have hypotheses. So see if you have a null and alternative ready. What would the null equal? What's the default? If you said 5, you're right. So then what is the alternative? Well, the sample is smaller, and we want to say, is there convincing evidence that aquatic life is at risk, meaning that the dissolved oxygen level is lower than 5. So if you said mu is less than 5 milligrams per liter, you're correct. So that is your P part, the first part of pass. We're going to set an alpha equals 0.05 level since it's stated. Let's check our conditions. Random. Where does it say random? Right there, 30 randomly chosen sites along the stream. 10%, streams have a lot of water. So 30, not even putting a dent into the 10% of it. So we've met the 10% of all locations in the stream. Not even close. So now let's look at the approximately normal. Nowhere in the problem does it say anything about the levels being approximately normal, but we don't have a graph of the data, so we can't really say anything about it, but we have 30 data points. That's a strong sample size. So our sampling distribution is going to be approximately normal because the central limit theorem says we can do that, right? Anytime you have a sample at least 30, you can say the sampling distribution is approximately normal. Pause to write that down. So that's your non-calculator work. Now let's transition to the calculator work. All right, so at this point here, we're gonna stick to our stat menu, and I'm done kind of going through teaching things by hand. We're gonna stick with the stat menu, do the more precise tests and intervals. So that's what I'm gonna do on the check understanding. So before I reveal that, you should have tried to put these numbers into your calculator. So see if you can run the test on your own. All right, you should have identified this as a t-test. There's one sample. We don't have the raw data. We have statistics. So in our statistics, your null is 5. Your sample mean is 4.77. Your sample standard deviation, 0.939. And your sample size was 30. So all that was given to you in the problem. We didn't have to actually figure anything out. The direction, since it's less than, we're going to go down here and select the less than. And we're going to go down to calculate. You ready? Here's what we have. We have a t-test statistic of -1.34. We have a p-value of 0.095. So it's not super small, and with our mean and standard deviation and sample size. So all that should help you summarize the problem. So what we're going to write is, we're going to write first, we're going to report our t-test statistic. We're going to report our p-value. Those are the two most important things from the test. We've already named the test, but you could go ahead and say we ran a one sample t-test and here are our results. It's not going to hurt you to rewrite these things, but you're not going to get any more credit for it because these problems were already, at least the mean and the standard deviation were already in there. Now you can write the degree of freedom. It's just 29. There's one sample, so we don't have to worry about the the more complicated degree of freedom. You're not required to make a drawing, but you could just to get a general idea of where that percentage is coming from. So in a t-distribution, 0 is the mean. If you go 1 below and you're at -1.34, that's somewhere around here, and that's roughly 9.5% of the shaded area below. So it's not super unlikely that that sample could happen. And because it's higher than 5%, we have to compare it to that. We're going to make our conclusion. So what do you conclude? I say since the p-value of 0.095 is greater than your alpha, we fail to reject the null. That means we do not have convincing evidence that the dissolved oxygen measures are less than 5 milligrams per liter, putting aquatic life at risk. So we assume that the stream is good, essentially. All right, well, that is the lesson. You can work on your sapling, but I want to show you something here, just some things to kind of keep in mind. I know that it might be confusing that we have 2 tests for T, 2 intervals for T, 2 tests for Z, 2 intervals for Z. There's a lot going on, right? So just remember that if it's a Z test, you're always going to be using sample proportions. If it's a t-test, you're always going to be using sample means, Z versus T. And to kind of help remember that, I've seen this come around before, zap tax. So if you think of zap tax, zap, ZP, TX, the X for the sample mean, P for the sample proportion, that might help you remember it if you kind of hit the buy, because nobody wants to pay taxes, right? So zap tax. Another couple things, in the back of your textbook, there is a fantastic summary for inference. I want you to be aware of it. So in the very back of your text, not the super back end, but like near the back, there's a section called IS2. It's also in the online textbook. It gives you an inference summary where the textbook uses the state plan do conclude method, which is the same thing really as pass. So whether you do state plan do conclude or PASS, you're doing the same things. And it gives you a real nice breakdown of what to do with what. So let me talk you through this real quick. If you're given, if we're working with proportions, if you have a one sample proportion, one sample, if you're trying to estimate, we use an interval. So that's this right here. And this is the calculator speak, one prop z interval. So when you go into your test menu, you look for one prop z interval. If you're trying to test a claim, we run a test. And this is a one prop z test. So there's the interval and the test statistic, but you know the calculator will give you the interval and the p-value if you run those in there. Remember the conditions for them are random, 10%, and for proportions it's large count. Remember? So NP and N1 minus P are both at least 10. That's your normal conditions for those. So again, if you want to estimate a claim or estimate a proportion versus testing a claim about a proportion. Again, with more proportions, if we're having two samples here, it's the same thing. You're still going to use a two prop z interval for proportions versus a two prop z test. And what's the difference? Well, with a proportion, you're going to estimate the true difference in proportions, estimate the difference in proportions. And for a test, you're going to test a claim about the difference in the two proportions. So just based on the wording, really. And the conditions are the same, but remember for two samples, we have to check conditions for both of them. So both of them are random, both of them are less than 10% of the population. And for the large counts, this is, you got to be careful because for intervals, we just use the sample proportions because we don't assume in an interval that they're equal. But in a test, we use the pool. So remember for test, there's that PC. We did that in the last unit, but it's worth mentioning now because we got to be very careful about our output values when we run these in the calculator. What we learned this unit so far was doing the same thing but with means. So again, for intervals, you want to estimate. So we're estimating a parameter, estimating a mean, versus a claim for a test. And your conditions for them are random, 10%, and the normal or large samples. So remember with the normal, it's either the population is normal, sample is large enough, or if not, your data shows no strong skewness or outliers. So that's the same for one sample, for a mean, or a test, for an interval or a test. Again, t-interval is the name for one sample, and t-test is the name for one sample t-test. And then to wrap it up, when you have means for two samples, we have two-sample t-int, two-sample t-int interval, and two-sample t-test. Same conditions, random, 10%, and approximately normal. Estimate the true difference in the two means versus estimate a claim about the difference in two means. In our next lesson, we're going to learn about something called a matched pairs data. So we'll get more into that, in the next lesson. But basically, we're either going to be using a t-interval or a t-test. So you'll understand the difference in those when we do the lesson there. But there is one more inference for means, and that's a matched paired data. All right, I hope that was helpful for you guys, and you can do your sapling assignment now. Thank you for watching this. I appreciate you all, and have a great day.